after his presentation. But I'll go ahead and get started. So Dr. Jeff Johnson has been a professor here at USF in the Department of Computer Science for the last 4 years. He holds a bachelor's from Yale and PhD from Stanford in psychology, and has worked as a UI designer and implementer, engineer manager, usability tester, and researcher at a variety of well-known tech companies here in Silicon Valley. In addition to teaching at USF, he's also taught at Stanford and Mills College. And today, Dr. Johnson will be talking about his book, The Psychological Basis for UI Design Guidelines. And if I've made any mistakes in what I said, I'm sure he'll correct me. So I'll turn it over to Dr. Johnson. Thank you so much for being here this morning.
Thank you. What I'm going to be doing is giving a talk about, so you're all computer science undergrad or graduate students, and I'm going to be giving a talk about psychology, which may seem like it's a strange topic to be giving in a computer science seminar, but this is psychology specifically intended to allow you to understand where user interface design rules come from. So why do we design user interfaces the way we do? Because people are people, and people have specific ways that they perceive the world, and which people think and remember things. And so that's what we're going to be talking about today. So let me share my screen with you so that you can see what I'm talking about here. Okay, so there's the title of my talk. You should be seeing that now. Not if you're seeing the title of my talk, please, so that I can make sure I'm sharing the screen correctly. Okay, great, thank you. All right, so people who do front-end design and user interface and user experience design are familiar with design guidelines like these. These came from a guy named Ben Schneiderman at the University of Maryland, and he first published the user interface design guidelines in the late 1980s, 1987, and then he's published updates of his guidelines every 10 years or so since then, and they've remained remarkably consistent. They've stayed more or less the same. And but you know, of course, computer technology has changed a lot since 1987, before most of you were born, probably before all of you were born, and and so you know, these are the kind of design guidelines that user interface designers, front-end developers, have used to guide their design of front ends. And so things like strive for consistency, cater to universal usability, prevent errors, permit easy reversal of actions, make users feel that they're in control, minimize short-term memory load. And so those kind of guidelines have helped people design computer systems since, like I said, 1980, the 80s. And here's another set of guidelines from another author. And they're actually, even though the wording is different, they're actually very similar to the guidelines that Ben Schneiderman put forward. And so one would wonder, you know, did the author Stone et al., did they copy from Ben Schneiderman? And the answer is no, they didn't copy. The reason that these guidelines tend to be the same, regardless of who publishes them, is that they're based on us. They're based on people, how people perceive the world, how we think, how we learn, and how we act. And so because people are a particular way, the design guidelines are going to be the same regardless of who puts those guidelines forward. So the other thing to know about user interface design guidelines is that they're not rote recipes. That is, you can't just, like if a recipe for a cake, if you follow the recipe, you'll get a good cake. But user interface guidelines are not like that, because you have to sort of understand you have to understand the terminology of the guidelines, first of all, but you also have to understand where did the guidelines come from? What is the basis of this guideline? So for example, if we say minimize short-term memory load, what does that mean? What is short-term memory? What is long-term memory? What kinds of memory do people have? And what does minimize it mean? You know, what does it mean to minimize short-term memory load? So that's more or less what this talk is going to be giving you some background in. Because if you try to follow user interface design guidelines, what you'll find is that you often face a conflict. You know, you'll have one guideline that says make it as high res as possible, and then you'll have another guideline that says make it as fast as possible. And you may not be able to do both of those things because there might be constraints on the implementation, right? You can't necessarily make something super high res and fast. So you might have to decide how fast is fast enough, or how high res is high res enough? What sort of delay can people tolerate? Those sorts of things. And so in order to understand that, you have to know something about human psychology and perception. So what we're going to cover is a subset of what this list that I'm going to show you here, because I have 45 minutes, including question and answers, I think, something like that. And so we'll only cover some of these. The book covers them all. But for human perception, we're going to talk about, the book talks about how perception is biased, how vision is optimized to see structure, etc. This is a list. I won't necessarily read it to you. And then human cognition, how we think. Attention is limited, memory is imperfect, limits on attention shape our thought and action. Hand-eye coordination follows rules. Human decision-making is rarely rational, things like that. And so that's what the book covers. I have 45 minutes, so I'm going to cover a small subset of those things. So let's start with perception is biased. What you see out in the world and hear and feel and touch and taste, it is not real. It is not reality. It is based on reality, but it is not exactly reality. Human perception, in fact, mammalian perception, is biased by your past experience. So things that you've experienced before bias your perception today. The context, the current context, biases your perception, and your future goals, what you intend to do, all of those things bias your perception. So let's look at an example of that. So how many of you have heard of the painter, let's see, just a second here, Jackson Pollock? How many of you have heard of Jackson Pollock? So Jackson Pollock is a painter that has a great gig. He gets to splatter painting onto canvases and get paid a lot of money for it, and his paintings go into museums. And so he gets so here's some pictures of Jackson Pollock doing his work. I wish I, could be paid that much for splattering painting onto canvases. All right, so now I'm going to show you a Jackson Pollock splatter painting, and I'm going to show it to you very briefly. Okay, so that was, you conceive of that as ink splattered onto a canvas. Now, did anyone see something other than a random splatter painting? Did anyone see something other than that? Okay, so now I'm going to give you another piece of background. I'm going to show you a picture of a dog sniffing the ground next to a tree. The dog is a Dalmatian. Okay, here we go. All right, does everyone see the dog? Okay, so there's the dog's head, and there's the legs, front legs, the hind legs, the tail's in the air. The tree is over here, the shadow of the tree and the leaves. are on the ground. So this is, so when I told you that this was a Jackson Pollock splatter painting, you saw a random collection of dots on a screen. But when I showed you told you that it was a picture of a dog sniffing the ground next to a tree, then your brain organized the picture differently. So that's an example of how past experience, which is the stories I told you, can affect your perception. Here's another example. So this is an example that is more related to computer interface design. So this is an example of what we call in user interface design a wizard. A wizard is a sequence of pages that carry out a sequence of steps. So when a user interface is going to be very complicated, what designers do is they often break it down into steps, and people fill out one step and then click next, and then fill out a next step and then click next, and then fill out the next step and click next, and eventually they get done. All right. So this is an app for a phone, and the app is for specifying limits of where your car can be driven. These are cars with GPS units in them, and parents can use this to track where their teenagers are going and make sure that the teenagers don't go outside of a specified zone. So you can specify a zone into which your teenage driver is restricted. Or you can also specify the zones in which your teenage driver is not supposed to go. So those are exclusion zones, and there are also inclusion zones. So here's the wizard for specifying a zone. The first thing they want to know is, what do you want to call this zone on your app? And so I'll say I want to call it Napa. So then I click next. Here's the next button. I click it, and I go to it wants me to choose a location from the map, from Google Maps. And so that's Napa, California, of course, because I called it Napa. And then it says, how do you want to specify the zone? Do you want to specify the zone as a circle, a rectangle, or as an arbitrary polygon? And I'll say I want to do it as a circle. So because I just care about the distance from home. That's all I care about. So then I click next, and it lets me specify as a circle, all right? And then this is strange, because if you watch someone using this application, they're likely to click this button over on the right, thinking that they're clicking the next button, and it'll take them back to the previous screen. Sorry. It'll take them back to the previous screen, and they'll wonder, why did it go back to that screen? And you tell them, I was watching you, you clicked the back button. And they said, no, I clicked the next button. And the reason that they were confused was that even though this says back, it doesn't say next, they're not paying attention to these buttons. They're paying attention to the lower part of the screen, where they're paying attention to their task, what they're trying to do. They're trying to set up a zone for their teenage kid. And so they're not paying too much attention to up here. And so they perceive the next and back buttons as being where they always were in the previous screens, okay? And so that's an example of how past perception can affect your current perception. Okay, so here's another example of bias. This is current context, not past experience, but this is current context affecting perception. So here we have two identical symbols, and if we put letters around them, the one on the left becomes a crooked H, and the one on the right is an A that's open at the top. The symbols are exactly the same, but your perception is biased by the context in which the symbol exists, okay, is shown. Here's another example. So this is called the Muller-Lyer illusion. So we take a line, we duplicate it, So we have two copies of the exact same line, and we put fins on them, and suddenly the one on the top looks longer to your eye than the one on the bottom, just because of those fins. So the current context is affecting your perception of the length of the lines. Here's another one. This is a famous one. So those blue lines, those blue stripes are actually parallel and flat. They're not slanted. Okay, and so but the way this the way this image is designed, it causes your eye to see the blue stripes as slanted. They're not. If you trace them with your mouse, you'll see that they're absolutely flat. Okay. Okay, so that's an example of current context affecting perception. Now I'm going to show you another example, and in order to do this, I have to unshare screen for just a second because I forgot to set a setting. I need to set a specific setting, and I will share the screen again and optimize for video. Okay, so now I'll share. Okay, so now I'm going to show you a video, and I want you to watch this guy's face. He's going to say some sounds, and I want you to watch his face. Okay, so here we go. Just a second here.
Ba 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 ba.
Okay, I paused it for a second. The sound, he was moving his lips differently, and so you probably heard ba 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 for the first one, and va 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 for the second one, and something else for the third one. I don't remember exactly what it is, but um, the actual audio underneath those clips is exactly the same. There's no change in the audio between those three clips. What is causing you to hear different things is the motion of his lips. Now, most of you might think that you can't lip read. In fact, you can lip read. Almost everyone can lip read. You're lip reading all the time. When you're talking to a friend, if you can see their face, that's affecting how you hear what they say. And so if you go into a loud music club, a nightclub, and you're talking to your friend across the table and there's a band playing and it's really loud, it helps you to be able to see your friend's face when they're talking, because you're really reading their lips, and that's affecting what you hear. So now I'm going to continue the video, and we're going to show the guy we're going to show three copies of the guy, and just move your eyes between one and the other, and you'll hear different things depending on which of the three guys you're looking at. And the sound is the same, it doesn't change.
Ba 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 ba.
Oops, it started over.
Ba ba
It
ba
started over, I'm sorry.
ba 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 ba.
Now I'm going to split them up.
Ba 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 ba.
So
Ba 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 ba.
okay, So if you looked on the right, he's saying ba, ba, ba. If you look in the middle, he's saying da, da, da. If you look on the left, he's saying va, va, va. But in fact, there is no difference between the sound. It's all the same. Okay, so let's, let me go back to regular sharing. And just a second, sorry. Share, stop share, share screen. And
ba ba,
oops, I
ba.
skipped this guy. Okay, so for some reason I have lost you guys. I was seeing you, and I got to find out how I can get that back. Where? Oh, stop share. Okay, there you are. There's everybody. And now I will go back to sharing my screen. Just a sec. Put that up. And sorry, just having a little bit of Zoom trouble here. Okay, there we go. So now I will share.
Bob.
Come on. Okay, so the other thing is that so I talked about how perception is biased by the past experience. Then I talked about how the current context, visual, hearing, affects your perception. And now I'm going to talk about how your future goals affect your perception, what you're trying to accomplish. That biases our perception. So adults' perception is focused almost entirely on your goals. People tend not to notice things that are unrelated to their goals. So for example, I'm going to show you the contents of a toolbox, and I want you to tell me if there are scissors in the toolbox. Okay, I'm going to show it to you very briefly, and I want you to tell me, are there scissors in the toolbox? So here we go. Okay. So I'm going to stop sharing for a second so I can see the responses. So could you see the scissors? Did you see the scissors? Nod your head if you saw the scissors. You didn't see the scissors. Okay, so some saw the scissors and some didn't. And so the next question I'll ask is, was there a wrench in the toolbox? Interesting. Okay, so usually most people can see the scissors because I asked you to find scissors, and but if I ask you to find something or tell me if something was there that I didn't ask you to look for, people usually have no idea. So let me go back to the slide. Okay, so there was scissors and there is a wrench. All right, so what does that have to do with user interface design? Well, what it has to do with user interface design is that people have goals. When they're trying to use a website or an app, they have something in mind that they're trying to do. And so they tend not to notice other things. So for example, if I put you on the homepage of the University of Canterbury, and I ask you to find information about financial support for postgraduate students in the computer science department, your eyes would start scanning. Basically, there would be sort of semi-random motion of your eyes around the screen. But it wouldn't be really random motion, because what would happen is your eyes would start to focus on certain things on the screen that had to do with the goal I gave you, which is to look for information about financial support for postgraduate students in the computer science department. So what would happen is your eyes would start to spend more time around colleges and departments, postgraduate students, and maybe you would start looking at the search box because you were thinking about doing a search. But you would probably end up going completely away from the page without ever noticing that you had been randomly selected to win $100, because nobody asked you to find that. Your goal had nothing to do with that particular thing. So basically, your perception is biased by your goals as well as by their past experience and the current context. All right, so now I'm going to talk about color vision for a second. So human color vision is not like a camera. A camera is what we see here on the right. On the right, basically, every pixel in the imaging plate of a camera has an imaging plate at the back of it. And every pixel has 3 light sensors. One light sensor is sensitive mostly to blue light, one light sensor is sensitive mostly to green light, and one is sensitive mostly to red light, and they are about approximately equal in their sensitivity to light overall. And so, if, for example, if a beam of light hits this pixel and it happens to be, let's say, 580 nanometers in wavelength, then it would hit, and the red sensor would fire at about this rate, and the green sensor would fire at this rate, and the blue sensor would not fire because we're not in the range of sensitivity of the blue sensor. Okay, and so what the camera does is it adds together the red response, the green response, and the blue response, and it produces what's called an RGB number, a red, green, blue number, which goes out, and that's recorded as the value of that, the color value of that pixel. Okay, the human visual system, in fact, the mammalian visual system, does not work that way. We have, most people have 3 light sensors, that is cones, 3 cone cells, and the cone cells are in your retina, and they detect light of various frequencies. And there are ones that are called low frequency or red sensors. There are medium frequency or green sensors, but notice that the green ones are less sensitive to light than the red ones are, and also they're sensitive almost over the same range as the red ones. And then there's blue sensors that are hardly sensitive to light at all, and they overlap as well. So this retina, this visual system, cannot work by adding together R, G, and B and giving an RGB value. That's not how it works. It doesn't work by addition, it works by subtraction. It subtracts. There are 3 channels of information going from your eye to your brain. One of the 3 color channels. One of them is red minus green, and the other one's blue minus yellow. Well, you don't see yellow on this, but yellow is actually a function. It's a complex function of green and red, and so basically, blue minus yellow is blue minus some function of green and red. So blue minus yellow, red minus green, and then there's another complicated function that goes back to your brain that is another, it's an addition and subtraction, and it ends up coming out with overall brightness. So the result is that the human visual system, and like I said, the mammalian visual system, is not sensitive to absolute light levels like a camera is. A camera is sensitive to exactly how much light there is in a room or on the outdoors. But the human visual system is not sensitive to how much light there is. It's only sensitive to differences and edges and changes. That's what the human visual system is sensitive to. So for example, if you look at this, the inner bar, the bar on the inside, is not light gray on the left and dark gray on the right. It is one shade of gray the entire way across. It's only one shade of gray, but it looks light on the left and dark on the right because the outer bar, the enclosing bar, is dark on the left and light on the right. So what your eye is seeing is a contrast. Here's an even better example. So this is a checkerboard And so notice the A square and the B square. The A square and the B square are actually the same shade of gray. There's no difference in the shade of the A square and the B square. And so I'll show you that by taking them in Photoshop, taking a little piece of each and magnifying it and pulling it out to the right. So I take a little cut of each and I put them out, and there they are, the same shade. Okay, but you don't believe me, you think I cheated. So I'm going to do it a different way. I'm going to cover that up, and then I'm cover that up, and then that, and then that, and then that, and then that, and then that. Okay, so when I cover up the contrasting information, your eye then reveals to you that they're the same shade. And what allows the B square to be the same shade as the A square is that shadow being cast by the cylinder. Okay, so that see, the thing is, your brain knows that checkerboards have light squares and dark squares, and it sees that the A is on a dark square and the B is on a light square. So you see the B square as lighter than the dark square, partly because of the fact that it's surrounded by dark squares, and also by the fact that the A is surrounded by light squares. So again, when I cover them up, however, and remove all the context, you can see that they're actually the same shade. So people have difficulty discriminating between pale colors. So if on your user interface, if on your app, tan means one thing and yellow means something else, then people are going to have trouble seeing the difference between it because of the way their eyes work. All right, and also because of some screens or some monitors may not show the colors as accurately as you see them on your monitor when you're designing. Okay, so you have to be very careful about designing so that color differences like this one are not do not convey important information. Okay, so, and another thing is that color patches, the size of a color patch influences how easily people can tell the colors apart. So it's hard to tell that these are two different shades when they're small, but when we make them bigger, it's easier to tell that they're not the same shade. And so that's another thing. As a designer, if you need people to be able to see the difference between certain colors, you have to make the color patches large, because if they're small, they won't be able to see the difference between them. And similarly, if color patches are separated, it's hard to tell the difference between them. And if you put them together, your human eye is designed for detecting differences in edges, and so it can clearly see the difference in color between these two squares. But if we move them apart, it's harder for it to tell the difference, because you have to move your eye from one to the other in order to see, and then your memory becomes involved in the comparison. You have to compare based on your memory of the color before you moved your eye to the other one. So what that says about design is that we have to make sure that people can tell, like when we use color to convey information, like here, this is another, like you're trying to make an airline reservation. And so you have to get your seats, then you have to check to say whether you're checking baggage, then you have to pay, and then you confirm, and then you get your ticket. You get your reservation, okay? So they're trying to show us that we're on step 3. But the problem with that is that they're using light green as a way of telling me that I'm on step 3. But that's not good enough, because some displays, like an Amazon Kindle, is not going to show that gray, and so people will not know what step they're on. And also some people have a certain kind of color blindness that will prevent them from seeing that square is the one, or that circle is the one that's colored in. And in a few minutes, I'll show you a better way to do it. So 8% of males have some kind of color blindness. There are different kinds of color blindness, but 8% of males have one or the other of the several different kinds of color blindness. 0.5% of females do. So for example, a friend of mine who is red-green colorblind can't tell the difference between these two lines. To him, they're exactly the same color, okay? I see one as dark red and the other one as black, but to him, they don't look different. And you might think, okay, so suppose these were stock charts, and one of them was showing Apple's price, and the other one is showing Google's price. And so what I see is one of them, and let's say this black one is Google. So Google's doing this, and it's going up and down and whatever, and then Apple is doing that, okay? But so you might think, okay, well, my friend, since he's colorblind, he can't tell which of these is Apple and which is Google. But it's actually much worse than that, because wherever they cross, he can't tell which one goes forward from that point, okay? So to him, this is a jumble. It's not even two lines. So the design principles that come out of that are, don't rely solely on color. If in your app or your website, if green means one thing and blue means something else, don't have a green circle and a blue circle, because some people won't be able to see the difference between the green and the blue. Instead, use a green triangle. In other words, use some cue redundantly with the color. So green triangle and blue circle, okay? There, it doesn't matter whether I can see the green or the blue, or to see the difference between the green and the blue or not, because I can see that one's a triangle and one's a circle, okay? So you should use other redundant cues. So for example, with that step indicator, what I would do if I were a designer is I'd first of all use a darker green, not that really pale shade of green. I would bold the number, I would bold the circle, and I would bold the word underneath it. So we have boldness in addition to the color indicating what step I'm on. So it doesn't matter whether I'm using a black and white display or a grayscale display or a color display, or I have color blindness, I'll still be able to see what step I'm on. All right, the next thing we'll talk about is peripheral vision. So human peripheral vision is bad. And so you get situations like this one when people don't know how bad human peripheral vision is. When designers don't know that, they design websites like this one. So this is Delta Airlines. And so I'm working down here. I'm selecting my seats and I'm clicking these buttons. And I'm not looking over here, and I'm not going to see that message hidden in this blue bar. I'm not going to notice this message because my eyes are looking over here. Now you might think, well, of course I see it. It's right over there. And that's in fact what some developers say who don't know about human psychology and peripheral vision. They'll say, it's on the screen, why don't they see it? And the answer is they don't see it because the way their eye is constructed. Human eyes are high resolution in the middle and low resolution everywhere else. So here are the cone cells we were talking about, and these are the rod cells. And this is the density of cells per square millimeter. So in the middle of your visual field, there's 158,000 cone cells per square millimeter. That's a lot. That's very dense. 158,000 per square millimeter, all right? But it falls off very rapidly. The density falls off very rapidly down to about 8,000 per square millimeter. And that's actually still pretty dense, but it's not 158,000. So like I said earlier, I was comparing digital cameras to human vision. Cameras, the visual plate or the photosensitive plate on the back of a camera has the same resolution over the entire area of the plate, but a human eye does not. It has only high resolution in the very center of its visual field, and everything else is low res. And you may be confused about that because you look around the room right now and you see everything in high res, but that's because your eye's moving, your brain remembers what things look like and creates a model of the world in your head that it's showing you, okay? So, but in fact, your eye is only high res in the exact center. And the exact center is very small. It's the size, if you hold out your arm, look at your thumbnail. Stick up your thumb, look at your thumbnail. Your thumbnail is the size of the high resolution area of your retina. Your thumbnail at arm's length is the size of the high resolution area of your retina. Everything else is low res. So peripheral vision is poor because, number one, pixels are much denser, high resolution is higher in the middle. Two, the cone cells in the center of your retina, which is called the fovea, by the way, the center of your retina, each cone cell sends a fiber out the optic nerve to the brain. Each cone cell, every cone cell sends one fiber. The optic nerve is actually a cable with millions of fibers in it. So every cone cell in the retina, in the fovea, in the center of your eye, is sending a fiber out. Whereas in the periphery, three or four cone cells join to send one fiber. So the way we in computer science would talk about that is we would say data goes from the center of your visual field to your brain uncompressed, and data from the periphery of your vision goes to your brain compressed with data loss. So so it's like you have a high resolution TIFF in the center of your vision, a very small area in the center, and you have a low resolution JPEG in the rest of your vision. And then third, when the information gets back to the back of the brain is actually has on it, the visual cortex has a map. It has a map of the retina, but the map is distorted. Half of the area of the visual cortex is devoted to processing information from that 1% little tiny center of your visual field, and the rest of it, the other half, is for the entire other 99%. Okay, so because of that, because pixels are denser in the fovea, data from the fovea is uncompressed and data from the periphery is compressed, and half of the visual cortex serves the fovea, the resolution at the center of your vision is 300 dots per inch at arm's length. But the resolution at vision's edge is much lower. It's more like 3 dots per foot. 3 dots per foot, not inch, okay? And so that means that the size of a pixel, the effective size of a pixel at the edge of your visual field, right, just where you can just barely see things if you hold your arm out to the side, that the size of a pixel is the size of a melon at arm's length, okay? So, and you don't believe me, you think you have high resolution everywhere in your visual field, but I'm about to show you an example that will disprove that. So look at this chart and tell me how many dots are there? How many black dots are there? The thing is, you can't see them all at once. Your brain is filling in information for you that it's seeing in low res, and only where your eye is actually focusing do you actually see the dots. Okay, this is not a video. This is a still image, okay? Those dots are there all the time, but you can't see them unless your eye is directly on them. Do you notice how many dots there are? How many? Somebody tell me. You can unmute.
12?
Yeah, there are 12 dots. So for example, with this, this dialog box, what would happen is somebody would click on this button, and the question is, will they see this error message that's appeared over here on the upper left? And the answer is sometimes, but mostly not, because this heading is also red. And so what the person's eyes see at the moment they click on this button, when they're presumably looking at the button, this is what their eye sees, essentially, something like this. So basically, there was red stuff up here on the left, and there still is. When the error message appears, it doesn't change anything. There was red stuff, and there still is. So there's no reason for the eye to move up there to see. On the other hand, if something green had appeared here, or something yellow, when they click that login button, then their eye would have a reason to move in that direction. So I'm just about done because we're running out of time. So I'm just going to show a couple more slides and then quit and ask for questions. So, so in the design rule that leads to is put things where the users are looking if you can predict that. You can't always predict it, but if you can, put it where you know that they're going to be looking. Put an error message near the error that the person has made. Use red for errors, and use error symbols to mark errors. So for example, this is a bad design because basically I'm looking down here and I'm not going to see this error message up here because it's not in a distinctive color, and because this is where I'm focusing. And my eye doesn't have high resolution up here because I'm looking here. Whereas this one, it's red, it's in the center, and it has an error symbol. Okay, and so another thing you can do is you can shake it. You can shake the error message so that people will see it like that. I don't know if you saw it wiggle. Okay, and that will draw the eye. That will cause people to move their eye and look. And the reason is because evolutionarily, if you didn't move your eye in the direction that something moved in your periphery, and your periphery is good at one thing, it's good at detecting motion. And so when your periphery sees something move, it drags your eye in that direction because it might be a leopard. On the African savanna, 100,000, 200,000 years ago, if you didn't move your eye in the direction of where you saw motion, you wouldn't be passing your genes on and we wouldn't be here. So the human eye is actually quite good at detecting motion in the periphery. All right, so I'm going to quit here and take some questions if there are any. So basically I was covering visual perception in the periphery. I was covering color perception, and I was covering how your perception is biased by past, present, and future. Let's see, any questions? Anyone have any questions? What I'm going to do is I'm going to give a copy of, well, John has recorded this session, so the session will be recorded and you can watch it later. But I also give a copy of my slides to John to post for you, okay? There were a couple of things I didn't get to cover because basically I ran out of time, and I have to teach a class in literally 5 minutes. So I can't stay for a long time and ask questions, but I can stay for another minute or so.
I can also pass questions on to Dr. Johnson if any of you afterwards have a question that comes up.
Yeah, that would be fine. I'll answer questions. You know, you can batch them up and send me an email, John, and then I will write the answers as best as I can and send them back.
Sounds good.
All right. Well, thank you very much. I thank you for your attention. Okay.
Thank you, Dr.
Bye-bye.
Johnson.
Bye.
Thank you.